All right, so how are you doing today?
Good, how are
Good?
you?
Perfect, thank you. So let's start what we did last time again. So now we're now doing something in the chapter 5. We talked about the stereochemistry. So if you want to do stereochemistry on certain compounds, it is important to find the chiral center. So chiral center is quite simple actually. If you can find any carbon in your organic compound that has 4 different groups on it, maybe you can have those. It's a chiral center. So even though you make a mirror image on that chiral center, it's not the same compounds because it's not superimposed with each other. So even though you rotate it, there will not be overlap in the same position for those 4 groups. Then you can find your chiral center. So once you find the chiral center, we actually gonna do Canning-Gold preload rule or convention. The way it's okay. To just figure out if whenever you have a chiral center, you want to just we use this one to just find out if that chiral center has R or S configuration. Okay. That's the job we need to do. This is also the reason why we talked about the optical property there. What's how many degrees that the polarizer can rotate through the sample, everything. We're all getting there with the RS configuration here. Okay. So let's try a little bit more on the how you're gonna use the Canning-Gold preload convention to find out the S or R or S configuration here. So if you have like organic compounds, it looks like this. Okay. Okay. Here, so we have 2-bromobutane, right? So we have this compound over here, and then the first job you need to do is try to find that the chiral center first, right? So if you look at this carbon over here, this is a terminal carbon. So I didn't write it here, but you'll see the 3 implied hydrogen there, because it's not shown there, but you will see this implied hydrogen here. But it has 3 same hydrogen over there. So this obviously cannot be your chiral center. So same here, this is also terminal carbon, cannot be a chiral center. And this one has 2 different groups here and here, but it has 2 same hydrogen on here, so it cannot be chiral center either. Okay, but for here, you do have chiral center. So you have this carbon right here, and it has a bromine here, and you have like 2 carbon groups on here. You have only 1 carbon on the other side. You have a hydrogen. So it's all 4 different groups on this carbon here. Makes sense, right? So this is our chiral center. So we found it. Oh, here's our chiral center here. So then, only thing you have to do is you have to prioritize the 4 different groups. Basically, you're gonna use an atomic number. Okay, so you're gonna use atomic number. So if you look at the periodic table, which will be given in the exam, you can find the bromine somewhere down on the right side of your periodic table, which is pretty much higher number in atomic number than other carbon and hydrogen and so forth. So that is why this group will become first. It's the private groups. And then the problem here now, let me just do this again. So the problem here is those 2 groups are tied in atomic number because they're both the same carbon, right? In this case, what you need to do is go further from there, meaning So this is a tie in here. Well, now we're gonna go to the next ones. Okay, next ones. And then you have, once again, you have a 2 hydrogen and 1 carbon bond to this carbon here. Okay? So this will be CH, H. Okay? And this one is the hydrogen, hydrogen, hydrogen. Hydrogen, hydrogen, hydrogen. So because of the carbon is still higher than what? The higher in the atomic number than one of a hydrogen. So this will be prior to this one. So this will become 2 and 3. Because the carbon is higher than hydrogen. So if you go from that, the same carbon, it'll be carbon, hydrogen, hydrogen. They're only hydrogen, hydrogen, hydrogen. So this will be higher in priority than this one. This is carbon. Makes sense, right? Good, perfect. And obviously, this is the lowest number you can find in the Cunningham Taylor convention. So this will be number 4. Okay. So if you did all prioritizing the 4 groups, only thing you have to do is assuming your least prior group, which is number 4, heading backside of where you're looking at. So meaning you see this the dashed line. We talked about this on several times already. This means if this is in the plane, that we writing this compound structure on this blackboard here is heading backside of the blackboard. And if you look at those lines, just regular lines, it's just parallel to this 2D. They literally heading this way, and the hydrogen is going this way. Okay? And then if you look at this wedge line, it's actually going toward to you. So if you're looking at this one, the bromine group is actually heading toward to you. Okay? So in this case, only thing you have to do is try to put number 4 on the back, which is already there. So you don't have to do anything, just follow the 1, 2, 3. So this is the where you see the direction 1, 2, 2, 2, 3. Okay. So if it goes in clockwise, we're gonna do. This is the R configuration here. So whenever you do this one here, you can actually do. This is R2 bromo butane. Okay, so this will be more specific and nomenclature. Okay, makes sense, right? You get perfect. So how about we change the position a little bit? Okay, so if you do this one, okay, in this case, we actually change the position of these 2. So as we know, this is number 1, this is number 2, this is number 3, and this is number 4. Okay. So in this case, if you do this one, 1, 2, 3, this way as well. Okay. So this is also clockwise. So this looks like it might be odd configuration, but the problem is your number 4 should be heading backward, like in the other side. But now it's heading toward to you, right? When you look at it in the face. So what it actually looks like is this one. Consider this red is number 4, okay? And then the most blue is number 1. Less blue is number 2. And the least blue, which is white, is number 3. So you're only going to use number 1, 2, 3, 4 as configuration. But number 4 is just to determine where you need to look at. Okay. So in this case, this is actually heading toward to you, right? 2, and your number 1 group is heading back. So this is the plane. This is heading toward to you now. This is heading back, right? And then you have number 2 right in this plane here, number 3 right here, right? Okay, so now we looked at it before like this, because the hydrogen was on the back. Now it's in the front, you need to look at it here. So actually, so if you look at it from here, it's still R, right? 1, 2, 3, clockwise. But you can look at it from the other side, because this one has to be on the back when you look at it. So it's actually not 1, 2, 3, 1, 2, 3, the other way. Make sense, right? So if that is the case, whenever you do this, one trick you can do, just prioritize the way it is. And if you look at the number 4 is on the back, okay? When it is on the back, just flip it. And that is S configuration. Okay? So once you find out the way that rotating by following the higher or to lower prioritized groups, and then when you see the number 4 is heading toward to you, just flip it. So it was once R, but indeed it was actually S configuration. Okay, that's pretty much it. Okay. Kind of makes sense, right? Kind of makes sense. So here's the. So most of the time you're gonna see the number 4 group, which should be most likely hydrogen, either back on the front. So it's on the back. Just count the prioritized group 1, 2, 3, and just choose the person. One trick I can tell you is I don't know how you write the R, but I do write this one in this way. So do you see this? I write the R this way. And obviously you'd write S this way, right? This one. So you never forget which way is R or S. Because if you write in this way. Okay? Makes sense, right? So anyway, so that is the case, but this is the most of the time. You're gonna see the number 4 either heading toward to you, front or the back. 2 case. What might be the most difficult case then? So let me draw the if I draw in this way, your number 4 groups are on the plane, right? That might be really tricky, because you don't know clearly from here where it's heading, because it's on the plane. Makes sense, right? So in this case, if you do some practice, you can actually see it. But if it's your first time, I always use your pencils, 4 pencils, maybe for different colors. That would be better. So I'll do the same. Okay. So if you in this case, this is very tricky because you don't know it's heading up the front or back. Okay. So I'm gonna do the same with the pens. So this is our red. Okay. So I'm gonna here because it should be in the same plane. And number 2 is also has to be on the same plane. So I'm gonna put this number 2 right here because it's on the same plane. Okay. And then the number 3 is heading toward to you. Okay. And your number 1 is heading back. Okay. And then only thing you have to do is you have to look at it from here. Right? So if you look at it from here, only thing you have to do is so what is it? Is it R or S? 1, 2, 3. R. Yeah, there you go. So it is hard. I totally understand. If that is on the plane, because if you're either heading back or front, it's very easy. Either you just need to find the R and S, or just flip it, invert it. But if it's on the plane, you can try to do it with your pencil and C is R or S. Okay, and then I don't know if you're gonna believe it or not. If you do this quite many times, you can actually do it in your head. Like imagine yourself looking this compound from here. Then you can actually do it in your head, in your mind. That would be so awesome to do because it's really hard to look at something that is in the paper in a 3D. That's quite a skill you need to learn in organic chemistry. Makes sense, right? Okay. But to be honest, I don't think I'm gonna put this on the exam. But this will be really helpful for you to start thinking about some compounds in 3D in your mind without drawing this 3D models. Can I move on? Okay. So I will just give you more. So we find out some RS configurations on the compounds. Okay? But let's talk about something that's a bit more complicated, just slightly more. Meaning, what if we have more than 2 chiral centers? Okay? So let's try to make some compound looks like this. Okay, so okay. So yeah, this is the 2-amino 3-hydroxy butanoic acid here. And if you look at this one over here, you have 2 chiral center over here and over here. Can I draw this again? I think because of the light, oh, actually you can see it. So, okay. So anyway, what I'm gonna do is I'm gonna try to write the mirror image to this one. So I'm gonna just do the same, but just a mirror image. Okay. Come on. Okay. This is the same thing as this one. Okay. So if you draw the mirror image, it looks like this, right? You guys see this one here. Okay. So if that is the case, let's try to do the RS configuration on these 2 first, and this one. Okay. So obviously you have a nitrogen over here, carbon, hydrogen. Okay. So if you look at the periodic table, which one might be the number 1? Is nitrogen, carbon, hydrogen. Atomic number, which is nitrogen. Perfect. Nitrogen is number 1. Makes sense, right? Number 1. And also the problem is you have a carbon over here. There's tie with those 2. Okay. So let's do one step further. Okay. So this is the number 1, obviously. This is obviously number 4 because there's no, this is different in atomic number. But these 2, these 2 has this one. So this is the tricky one. You have a carbon making a double bond to oxygen over here, right? In this case, you count this oxygen twice. So so double bond is still 1 bond, but for counting Golden convention, you count them as like 2 bonds. Okay, it's tricky, I know, but this is just the way we do it. So it's not just OO, it's OOO. Okay, so it will be OOO. Okay, and here you have a carbon here with O. Carbon, hydrogen over here, right? So it'll be O with hydrogen over here. So if you compare the combination of those 3, this is a higher, right? This is a higher, right? Okay. This is higher, so this will be number 2. This will be number 3. Okay, and this is number 4, sure. Okay, makes sense, right? Okay. So when you go here, so we will try to go do 1, 2, 3. Okay, 1, 2, 3. Because it's 1, 2, 3. So going this way. So that is the what? This chiroid center will have counterclockwise, so it will be S configuration. Am I right? Oh, almost right. Almost right. Why? Because your number 4 is heading toward to you right now. You see this, the hydrogen is on the wedge. So you have to look at it not here, here. So then you have to invert it to R. Tricky, right? It's pretty tricky, I know. So you just prioritize the groups here 1, 2, 3, and then you need to also look at the number 4. Because if your number 4 is heading back, oh, that's good. You don't have to do anything. But if your number 4 is heading toward to you, meaning you have to look at actually not here, but here. So you have to invert the configurations to the other. So it always wants S for sure, but it has to be inverted to R because the number 4. Okay? Makes sense, right? It's okay. So this chiroid center, for that region, we have a R configuration on this carbon here. Okay? Let's do the same over here. Okay? So we have number 1 over here, number 1 over here, and then you also have carbon here. Okay? And this is obviously number 4. Okay? This is a hydrogen. So oxygen will be number 1. From here, this is H, because there's 3 hydrogen over here, right? But this will be nitrogen, carbon, hydrogen. So this will be higher than this one, because it's nitrogen, carbon, hydrogen. So nitrogen, carbon, hydrogen is much higher than hydrogen, atomic number, right? So this will be, from this chiroid center will be 2. Okay, so this is number 3 then. Okay, so let's do this again. 1, 2, 3. 1, 2, 3. So this is also S, counterclockwise. But the problem is, once again, what's the problem here? This is also heading toward to you. So S also inverted to R. Okay, can you guys see this one? Okay, so it is definitely require some practice. That is why we're gonna do some dry lab for this one. We're gonna do a lot of practical problems within your lab. You're taking lab course, right? That one, but it will become more easier and easier if you try more and more here. Okay, so here's the thing. If that is the case, now you have a 2 chiroid center, not just 1. Okay, so if that is the case, if you just make a mirror image, which I just did, just based on what it looks on the mirror, so I just pointed into other side, same. So now they're in the different the other side, but all different way. So it's a mirror image, and then if you find out the RS configuration of those 2, you just know those 2 automatically if it's mirror image to each other, which is S and S. You don't even have to do the Huntington convention. Because when it's a mirror image, once again, this is what we call enantiomers, or some people call enantiers. Whenever you find that the RR configuration on this compound, when you try to draw the mirror image, you're going to find it's all embodied on those chiroid center to the other. So it'd be once RR, but the other side of the mirror is SS. You don't even have to do it. It's just the way it is. Once they're enantiomers to each other, if they're mirror image to each other, when you do the RS configuration, it's always going to be embodied into the other. Okay. So yeah, kind of makes sense. Okay. So Do you have any questions so far? You can also do prioritizing everything, but we'll tell you the same anyway. You will be asked this. So you can prioritize either R here, 1, 2, 3, 1, 2, 3, but hydrogen is still front, so it'll be going this way, which is S. Same here as well. You can try. Trust me. Read 1, 2, 3, but invert to S. 1, 2, 3, but still invert S. Okay. Do you see actually? Okay. So you can practice this one real quick. Okay. And here's the thing. So if these two are the mirror image to each other, maybe they can have enantiomers that shows the exact those 2 points is the invert each other. If you have, let me draw another compound real quick, okay? And I'm gonna draw the exactly same on this chiral center, okay? Okay, so this chiral, just finish this one real quick. Okay, if you do this one here, this is R, right? R, and this is the same, right? Here and here. So it will be, this will be still R, but this part, there's some IP you can do it. It's a mirror image on this half of it, not all. So this will be S. Okay, so well, whenever you have a 2 chiral center, R, if you do the configuration on the other compound as S and S, that's the enantiomers. Okay, but if you do it this way, you're only changing one of them, right? You're only changing one of them out of 2. In this case, they're not mirror image to each other, obviously, right? But still, they share the same bonding on those each carbons. So we call this diastereomers. So diastereomers is only possible when it has more than one chiral center. Because it only has one chiral center, either you're going to have a same or enantiomers, right? That's the only change you can make. But the thing is, if you have a more than one chiral center, you can either do enantiomers, but also what? Only one that embodied two. So in that case, we call them diastereomers, diastereomers or diastereoisomers. Kind of makes sense. So it's not total mirror image to each other. Just only one chiral center is embodied. See the. So maybe I will give you more example. So if you have a 3 chiral center, okay? If you have a 3 chiral center, you have a S, S, R. These are diastereoisomers because they're all embodied in here, but one is the same. So it could have been what? Enantiomers to each other. But because of this one, they're not mirror image anymore, so there can be diastereomers. Okay. So this will be still also what? Diastereoisomers as well. Okay, but this one, they're same. Makes sense, right? Kind of. Okay. See. I'm so sorry, but I'm gonna confuse you once more. So be prepared for this one. I'll probably do it once more next week. But this will make sense though. Oh, we good? Do you have any question about? Okay. So let me confuse you just one more, and I promise that will be all for the stereochemistry. Well, for now. If you are you taking over too next semester? you'll learn even more. But for now, this is the last one. I mean, kind of last one. So if you have this type of compounds, okay? Okay, so if you have this type of compounds over here, right? And you can also try to do the mirror image of this one. Okay. This is what we call tartaric acid, but yeah. Anyway, so this is the okay. So as you can see, these are mirror image to each other, right? This is a mirror image to each other. Okay. So okay. So if you do this one over here, you're going to have number 1 over here. Okay, number 1 over here, and this one. I'll rewrite this one in here. Okay, this will be 1. So in this case, this will be 2 carbons. This is number 4, right? Okay, and then this is going to be not OO, but will be OOO. Okay, remember this, right? OOO. And this carbon will be what? Tie in those 2 carbons from here, this chiral center. This will be OCH. Okay, so this will be still higher than this one because oxygen, right? So it'll be 2, 3, and 4. But once again, your number 4 is heading toward to you. So even though it's rotating in this way, counterclockwise, it will be still what? The R, right? Because you're gonna invert to the other. Makes sense, right? With one's S, but because of the number 4, so you don't even have to do this. It's just S over there, right? Okay. And then let's try to do this one same pretty much on this here. This will be 1, 2, 3, and 4. Okay? Same, because we had the same groups on here and here. Okay? So it'll be 1, 2, 3, okay? In this way. So it'll be S, but once again, your hydrogen in the front, so it'll be R again. Okay? So it'll be 1, 2, 3. So it'll be S, but this is front to you, so 4. Okay. So then this is also going to be S, right? No problem, right? It's pretty much the same what we did, right? Do you guys see it? So 1, 2, 3. So S, but this is in front, so we flip it this way. We good, right? Okay, perfect. So if in this case, we know it's S over here, right? So let's try to do one more. Okay. 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 So do you have so now this is the S, this is R, okay? See that, right? And then they're mirror image to each other, right? So there are also enantiomers. Am I correct? Okay, because these are mirror image to each other. If you do say these are mirror image to each other, enantiomers, you're actually wrong. Because if you look at this one very carefully, they're same. If you look at this one very carefully, they're same. If you just rotate this one to 180 degree. Do you see it? You just rotate it 180 degree. Same. So the problem is what's going on here, right? We just draw the mirror image, and it has a two chiral center, right? So I told you already, if that compound has chiral center, whenever you make a mirror image, you should have a different compound. That's what I've been telling you today, right? But this one is not. They're same, even though they do have a chiral center, and they are the mirror image to each other, but they're same. So we call this, in this case, we call this meso compound. Meso compound. Whenever you have a meso compound, whenever you have some plane in the middle that makes symmetrical to each other. So if you can have some plane that divide the compound in half, and their two sides of the compound is symmetrical to each other, we call them meso compound, meaning they're not chiral, they're achiral, meaning they even though they do have a chiral center, mirror image will be still the same thing. So this is a kind of special case. We call this a meso compound because even though they do have a chiral center, that case they're still making the same compound on the other side of the mirror. Meaning they are actually superimposable to each other, but if you just rotate it, they overlap on the same side, same position in all the way. Okay? All right. Okay, makes sense, right? Okay. So only thing you really need to know is if your compound is somewhere symmetric to each other, then even though you have chiral centers in the compound, those mirror images will still the same. So we call that meso compound. It's a special case. So meso compound is not chiral, it's achiral. They don't, even though they have a chiral center, they will not do the mirror image. Okay? There's no good. So only one more thing I want to do. So I'm gonna do just one more thing. Oh, we're almost there. We're almost there, I promise you. Okay, so this is the Colles tunnel. Okay, and then as you can see, there's so many chiral center. Okay, you have here, here, here. Oh, not here. I'm sorry. That's the two. Oh yeah, actually this is. Anyway, yeah. So you have so many chiral center over here, right? And then I'm gonna switch this one to this position. Sorry for my awful drawing. And then, oh yeah. But here, that is going to be here. Okay. So you see there's the methyl groups and hydrogen. Methyl groups, hydrogen are trans, up and down, up, so cis, same position here, right? And we call this Kupros tunnel. So they also have lots of chiral center, but if you do, only this position is what? Different in RS configurations, right? Only one. So there's so many chiral center, but only one chiral center is different here. And we name it differently. because they will show you completely different functions. Because even though only one chiral center embedded into the other, they change sometimes dramatically in functions. Because if you look at do you remember the decalin bicyclic compound? So if you look at this one over here, what it actually looks like is this. It's a trend, up and down, up and down, right? See, it's up and down. You see it, right? Do you see it? But in here, it's a trend. So it will be up, up. Here, so up, up. Equatorial up, axial up. Okay, do you see this? So even though one chiral center inversion that makes huge difference in what? Shape. Shape-wise, it's totally different compound, even just one. That's why it's so important to know RS configuration. Even one change make dramatic change, because any chance bio major? Whenever you think about the biological function, the most important thing is functional group, but also shape. That's why this is so important. So if you have a lot of the chiral center, but just one is different, that's very special, right? You have like so many chiral center, but just one chiral center is different. We call these two epimers. Epimers. So on the exam, if I give you 4 chiral center, but only one is different, you need to put epimers. You can also say diastereomers too, because epimer is one of the diastereomers too. But in this dramatic case, it'll be more specifically correct if you say epimers instead of diastereomers. I mean, it is diastereomers, but I would love you to say epimers will be more specific to be right. Yeah, I'll stop here today.